Hi friends, now we are going to discuss the three special case of damped harmonic oscillators. We named the three special cases: underdamped case, overdamped case and critically damped case. First we have to discuss underdamped case or light damping case. Here our damping constant is less than natural frequency. Okay, damping constant gamma is less than natural frequency omega 0. If so, the system is known as underdamped harmonic oscillator, or it executes underdamped oscillation. We know the general expression for displacement in the case of damped harmonic oscillator. That equation is x is equal to e raised to minus gamma by 2 c1 e raised to square root of gamma square by 4 minus omega 0 square into t plus c2 e raised to minus square root of gamma square by 4 minus omega 0 square t. Okay, here we take minus outside from both of these terms omega 0 square and gamma square by 4. Therefore, gamma square by 4 minus omega 0 square can be written as minus of omega 0 square minus gamma square by 4. Here also gamma square by 4 minus omega 0 square can be written as minus of omega 0 square minus gamma square by 4. Okay. Then here negative come inside the square root. If negative come inside the square root of minus 1 is I. Okay, we studied complex numbers, about complex numbers. Root minus 1 is I here. Therefore, x is equal to e raised to minus gamma by 2 t c1 e raised to root of minus 1 is I. Okay, imaginary part of the complex number. Okay, e raised to I square root of remaining part omega 0 square minus gamma square by 4 is there. Therefore, I square root of omega 0 square minus gamma square by 4 into t plus c2 e raised to minus root of minus 1 is I. E raised to minus I square root of omega 0 square minus gamma by 2 whole square into t. Okay, or gamma square by 4 into t. Okay, here let us take square root of omega 0 square minus gamma square by 4 is equal to omega 1. Okay, let us take square root of omega 0 square minus gamma by 2 whole square, or gamma square by 4 is equal to omega 1 here. Therefore, the expression for displacement in the case of underdamped oscillation becomes x is equal to e raised to minus gamma by 2 t into c1 e raised to I omega 1. This is omega 1. I omega 1 t plus c2 e raised to minus I omega 1 t, where square root of omega 0 square minus gamma by 2 whole square is omega 1. Okay, we have a mathematical relation that e raised to I theta is equal to cos theta plus I sin theta, and e raised to minus I theta is equal to cos theta minus I sin theta. Okay, we can substitute here e raised to I omega 1 t is cos omega 1 t plus I sin omega 1 t, and e raised to minus I omega 1 t is cos omega 1 t minus I sin omega 1 t. Okay, we can substitute that. Therefore, x is equal to e raised to minus gamma by 2 t c1 e raised to I omega 1 t cos omega 1 t plus I sin omega 1 t plus c2 e raised to cos omega 1 t minus I sin omega 1 t. Okay, that is x is equal to e raised to minus gamma by 2. From the terms c1 cos omega 1 t and c2 cos omega 1 t, cos omega 1 t is common, can be taken outside. Therefore, remaining parts c1 plus c2. Therefore, c1 plus c2 cos omega 1 t. Okay, first and third terms are joined here, c1 plus c2 cos omega 1 t, plus from the second and fourth terms sin omega 1 t can be taken outside. Remaining parts I c1 minus c2. Okay, therefore plus I c1 minus c2 sin omega 1 t. Okay, so x can be written like this: x is equal to e raised to minus gamma by 2 t c1 plus c2 cos omega 1 t plus I c1 minus c2 sin omega 1 t. Now we are putting c1 plus c2 is equal to x0 sin phi, and I c1 minus c2 is equal to x0 cos phi. So our equation becomes x is equal to e raised to minus gamma by 2 t into, in place of c1 plus c2 we use x0 sin phi. Therefore x0 sin phi cos omega 1 t plus ic1 minus c2 is x0 cos phi. x0 cos phi into sin omega 1 t. Okay, we know sin phi cos omega 1 t plus cos phi sin omega 1 t, that is equal to cos omega 1 t plus phi. Okay, here sin phi cos omega 1 t plus cos phi sin omega t, that is equal to cos omega 1 t plus phi. Therefore we get x0 is common, can be taken outside also. Therefore x is equal to x0 e raised to minus gamma by 2t cos omega 1 t plus phi. Okay, it is the expression for displacement in the case of underdamped harmonic oscillator. Here x0 e raised to minus gamma by 2t is the amplitude part. Cos omega 1 t plus phi is the phase part. Okay, this x0 e raised to minus gamma by 2t amplitude can be written as x of t. Okay, therefore our expression for displacement becomes x is equal to x of t cos omega 1 t plus phi, where amplitude x of t is equal to x0 e raised to minus gamma by 2t. Okay, this expression indicates that amplitude of this underdamped harmonic oscillator is exponentially decreasing with time. As time progresses, its amplitude will be decreasing. Okay, variation of displacement of underdamped harmonic oscillator with time can be represented like this according to the equation x is equal to x0 e raised to minus gamma by 2t cos omega 1 t plus phi. Okay, it is the representation of the variation of the displacement with time in the case of underdamped harmonic oscillator. We can observe that amplitude is exponentially decreasing with time. Okay, here we can observe an envelope, okay, by joining the maximum displacement points. Okay, that envelope indicates the amplitude here. Okay, that is exponentially decreasing with time. Okay, that is all about underdamped harmonic oscillator. Next case is overdamped case or heavily damping case. Here damping is very high, therefore damping constant is very much greater than natural frequency omega 0. Gamma is very much greater than omega 0. So square root of gamma square by 4 minus omega 0, square root of gamma square by 4 minus omega 0 will be a positive quantity here. Therefore square root of gamma square by 4 minus omega 0 is a real number. Okay, let beta be that a real number. Okay, therefore we know the general expression for displacement in the case of damped harmonic oscillator, that is x is equal to e raised to minus gamma by 2t c1 e raised to square root of gamma square by 4 minus omega 0 square into t plus c2 e raised to minus square root of gamma square by 4 minus omega 0 square into t. Here square root of gamma square by 4 minus omega 0 square is beta, which is a real quantity. Therefore expression for displacement becomes x is equal to e raised to minus gamma by 2 t into c1 e raised to beta t plus c2 e raised to minus beta t. It is the solution of the second order differential equation in the case of overdamped harmonic oscillator. Okay, by this relation also displacement exponentially decreasing with the time, because it consists a term e raised to minus gamma by 2t. Okay, therefore as time progresses displacement decreases. Not only displacement, amplitude also decreases, because amplitude terms c1 e raised to minus gamma by 2t and c2 e raised to minus gamma by 2t. Combination of c1 e raised to minus gamma by 2t plus c2 e raised to minus gamma by 2t gives amplitude here. So amplitude also exponentially decreasing with the time. It is the variation of displacement with the time in the case of overdamped harmonic oscillator. Envelope indicates the amplitude, both decreases with the time. Okay, that's all about overdamped case or heavily damping case. Now we are going to discuss the third case, critically damped case. In the case of critically damping, gamma by 2 is equal to omega 0. Okay, if gamma by 2 is equal to omega 0, harmonic oscillator is known as critically damped harmonic oscillator. Then we know the expression for displacement in the case of damped harmonic oscillator, that is x is equal to e raised to minus gamma by 2t c1 e raised to square root of gamma by 2 whole square minus omega 0 square t plus c2 e raised to minus square root of gamma by 2 whole square minus omega 0 square t. Okay, here this term gamma by 2 is equal to omega 0, therefore gamma by 2 whole square minus omega 0 square reduced to 0, therefore e raised to 0, here also e raised to minus 0 or e raised to 0, e raised to 0 is 1. Okay, therefore our expression becomes x is equal to c1 e raised to c1 into 1 c1 e raised to minus gamma by 2t plus c2 into 1 c2 into e raised to minus gamma by 2t. Therefore, x is equal to c1 e raised to minus gamma by 2t plus c2 e raised to minus gamma by 2t. E raised to minus gamma by 2t is common, can be taken outside. Therefore, x is equal to c1 plus c2 e raised to minus gamma by 2t. Let us c1 plus c2 is equal to c. c1 and c2 are constant. Their sum will also be a constant. Let c be that constant. Therefore, c1 plus c2 is equal to c. So, our expression becomes x is equal to c e raised to minus gamma by 2t. But it cannot be considered as a solution of this damped harmonic oscillator because it consists only one arbitrary constant. Okay, we must have more than one arbitrary constant, then only we can consider it as a solution here. Okay, so here we consider that gamma by 2 not exactly equal to omega 0 but very much close to gamma by 2 minus omega 0 not exactly equal to 0. But gamma by 2 minus omega 0 is it is a very small quantity, or gamma by 2 and omega 0 are very close to each other, not exactly equal. Okay, therefore square root of gamma square by 4 minus omega 0 square is not equal to 0, it will only be a small quantity. Okay, so we can take square root of gamma square by 4 minus omega 0 square is equal to h. H is very close to 0. It is a very small quantity. Okay, therefore our expression for displacement becomes x is equal to e raised to minus gamma by 2t into c1 e raised to, it is h, very small quantity. Okay, therefore e raised to h into t plus c2 e raised to minus h into t. Okay, e raised to ht can be expanded as 1 plus ht plus h square t square by 2 factorial plus etc. We know the expansion of e raised to x. E raised to x can be expanded as 1 plus x square by 2 factorial plus x raised to 3 by 3 factorial etc. Okay, here we use that mathematical expansion. Okay, so here we get x is equal to e raised to minus gamma by 2t into c1 e raised to ht can be expanded 1 plus ht plus h square by t square by 2 factorial plus etc. Okay, plus c2 e raised to minus ht can also be expanded like this. Okay, e raised to expansion of e raised to minus x is 1 minus x plus x square by 2 factorial minus x cube by 3 factorial etc. Here ht is in the position of x, so we get 1 minus ht plus h square t square by 2 factorial plus etc. Okay, but we said that h is very small quantity. Okay, therefore higher powers of h can be neglected. H square, h cube, h raised to 4 etc. terms can be neglected. Therefore our expression for displacement becomes x is equal to e raised to minus gamma by 2t into c1 into 1 plus ht, higher powers are neglected, plus c2 into 1 minus ht, higher powers are neglected. X is equal to e raised to minus gamma by 2t, c1 into 1 plus ht plus c2 into 1 minus ht. Okay, that is x is equal to e raised to minus gamma by 2t, c1 into 1 c1, c2 into 1 c2, therefore c1 plus c2 plus c1 ht minus c2 ht, ht is common in both of those terms, can be taken outside. Remaining parts c1 minus c2. Okay, c1 ht minus c2 ht can be written as c1 minus c2 into ht. Okay, put c1 plus c2 is m and c1 minus c2 h is equal to n. Okay, therefore our equation becomes x is equal to e raised to minus gamma by 2t c1 plus c2, a constant m, m plus C1 minus C2h is another constant n. Therefore, m plus n into t. X is equal to e raised to minus gamma by 2t m plus nt. Okay, that is the expression for displacement in the case of critically damped harmonic oscillator. Okay, if we look this equation, we can understand that displacement initially increases with the term m plus nt. As t increases, m plus nt also increases, so x also increases in the beginning of oscillation. But soon this term e raised to minus gamma by 2t dominated over the term m plus nt. So amplitude begins to exponentially decreases with the time, after time. Initially amplitude exponentially increases, but after some time amplitude exponentially decreases. Okay, initially amplitude increases by this term m plus nt, but soon after e raised to minus gamma by 2t dominate over this term, so amplitude exponentially decreases with the time. That's all about a critically damped harmonic oscillator. Now we are going to discuss the graphical analysis of a damped harmonic oscillator. Okay, graphical representation of a damped harmonic oscillator is given here. Okay, it is not exactly the similar graph given in the textbook. Okay, but a model of that. Here we have to first find the time period. Here we can study that, we can understand that amplitude is exponentially decreasing with the time. As time progresses, amplitude exponentially decreasing with the time, as indicated in our expression for displacement or amplitude. Okay, here we have to first find the time period. Okay, from this graph we have to find the time period. We know the expression for time period, that is time by number of cycles. Here, in order to complete 28.5 cycles, our damped harmonic oscillator takes 8 into 10 raised to minus 3 seconds, or 8 milliseconds. Okay, 8 millisecond is 10 raised to minus 3 second. So time period t is equal to 8 into 10 raised to minus 3 by 28.5. So t is equal to 2.81 into 10 raised to minus 4 second. Here we cannot count 28.5 number of cycles within 8 millisecond, because it is only a model. From the graph, if we consider the graph in the textbook, it is 28.5 cycles completed within time 8 millisecond. Therefore time period t is equal to 2.81 into 10 raised to minus 4 cycle. It is the time period of damped harmonic oscillation here. Okay, so angular frequency omega 1 here 2 pi by t1. 2 pi by time period is the angular frequency. Therefore here 2 pi by 2.81 into 10 raised to minus 4, that is equal to 22,400 second inverse. That is angular frequency here. Corresponding frequency can be found. Frequency nu is equal to omega by 2 pi. Here that frequency omega 1 by 2 pi, that is 22,400 by 2 pi, that is equal to 3,560 hertz. That is the frequency here. Okay, here displacement of the damped harmonic oscillator at the time Tc is Xc. Okay, displacement of damped harmonic oscillator at the time Tc is Xc. That Xc is, or we know the expression for amplitude, that is x is equal to x0 e raised to minus gamma by 2 t. Okay, here at a time Tc displacement is Xc. Therefore we can write the expression for amplitude like xc is equal to x0 e raised to minus gamma by 2 tc. But if we analyze the graph at a time tc, amplitude reduced to 1 by e times. Okay, amplitude reduced to 1 by e times of the initial amplitude x0, initial maximum amplitude x0. Therefore we can write xc is equal to x0 by e. Okay, displacement at a time tc is 1 by e times of the initial amplitude x0. Therefore xc is equal to x0 by e. x0 by e means x0 e raised to minus 1. Okay, so we can compare both of these equations. X is equal to x0 e raised to minus gamma by 2 tc and x is equal to x0 e raised to minus 1 can be compared. Therefore, e raised to minus 1 is e raised to minus gamma by 2 tc. Okay, so we get gamma by 2 tc is equal to 1. Gamma by 2 tc equal to 1 here. Therefore, gamma is equal to, damping constant gamma is equal to 2 by tc. Okay, gamma is equal to tc by 2. If we bring tc by 2 onto the right hand side, it becomes 2 by tc. Therefore, gamma is equal to 2 by tc. Here, tc is from in the graph, tc is equal to 5.35 millisecond. 5.35 millisecond. Therefore, damping constant gamma is equal to 2 by 5.35 into 10 raised to minus 3 second. That is equal to 374 second inverse. 374 second inverse. Now, we can find quality factor of this damped harmonic oscillator. That is quality factor. We know the expression for quality factor. Q is equal to omega 1 by omega. Here omega 1 is 22,400. Gamma is 374. Therefore, we get quality factor is equal to 59.89. 59.89. Now, we are considering radiating electrons in a small volume of hydrogen gas. If we consider the system consisting radiating electrons in a small volume of hydrogen gas, it can produce signal, okay, where damped harmonic oscillations are take place. Due to the continuous vibration of the radiating electrons, damped harmonic oscillations can be observed in such a system. There, electrons will be oscillating with a frequency 9.2 into 10 raised to 9 hertz, okay, with a very high frequency. Therefore, there omega 1 is equal to 2 pi into 9.2 into 10 raised to 9. Their quality factor becomes 2 pi into 9.2 into 10 raised to 9. There also gamma is 374, okay. Therefore, quality factor becomes 1.6 into 10 raised to 8 second. So, if electronic systems produce damped harmonic oscillations, quality factor will be very high. But in the case of atomic system, quality factor will be very small. Okay, in the case of atomic system, quality factor will be very small. But in the case of electronic system, quality factor will be very high. Okay, that's all about a graphical analysis of a damped harmonic oscillator. Thank you, friends.